nucleophilic strength can answer a lot of questions in this chapter and the next chapter. So we want to familiarize ourselves with what makes a strong nucleophile, what makes a weak nucleophile. So nucleophilicity has to do with kinetics. Stronger nucleophiles react faster. Strong bases are strong nucleophiles, but not all strong nucleophiles are basic. So OH, strong base, alkoxide, strong base, strong nucleophile. What about the iodide ion? That's the conjugate base of HI. So very strong acid, HI. So I minus is a weak, has hardly any base property at all. These are kind of weak. So basicity versus nucleophilicity. Basicity is defined by equilibrium and how badly it wants to abstract a proton. So the larger Ka equilibrium constant, stronger this base. Nucleophilicity is how fast can this reaction occur. So here are some guidelines we can commit to memory a little bit, and they'll help us not have to memorize all the nucleophiles and everything there is to know about them. A negatively charged nucleophile is stronger than its neutral counterpart. So both water and hydroxide can be nucleophiles, and this here has a charge, this doesn't. We know hydroxide is more nucleophilic than water. It's the equality sign greater. Same thing here, one period down on the periodic table. This ion is more nucleophilic than hydrogen sulfide. And likewise here, this ion a lot more nucleophilic than NH3. Nucleophilicity decreases from left to right. Alright, now life is a lot better. I'm glad I fixed that. So the larger an electron cloud, the more polarizable it is. So here is a polarizability effect. Fluorine, it's kind of a small ion compared to like the iodide. Fluoride, it's relatively small compared to iodide. So iodide has a big squashy electron cloud. Fluorine's a little more tightly held. So this thing's really tight. This one's loose. We say this is more polarizable than this one up here. And here it says sp3 orbital back lobe. So this is the back lobe to this orbital. And if I go to a pin, that looks more like a hybrid orbital. The hybrid orbital always kind of had a node. There's the node. Anyway, when these can overlap, they can decide to share electrons and form a bond. Bigger atoms have a soft shell that can start to overlap the carbon atom and form at a farther distance. Now, fluoride may not be the best nucleophile, but let's imagine it as a nucleophile. And here's our substrate, methyl halide. So if this is going to come, slam in there, form a new bond, and that leaves, that's our typical substitution reaction. And this is a Sn2 reaction. I can look at this reaction mechanism with the arrows and tell you it is bimolecular. This thing and this thing, two things working together. I see this arrow and this arrow simultaneously. It means it's bimolecular. If I double this, I'm going to double rate. If I double fluoride, I'm going to double rate. Now, for this ion to be in solution, looks like in an alcohol, it's got to be solvated. Here it's solvated, and we see hydrogen bonding occurring. So in order for this to happen, it's got to kind of kick this thing out of the way and get in there. So polar protic solvents have acidic hydrogens. We don't imagine them actually coming off and being protons. Of course, a proton around this would be even worse. It would be opposite charges attracting and making it not want to be a nucleophile anymore. But these acidic hydrogens can hydrogen bond. Here, hydrogen bond is being depicted. And this reduces the nucleophilicity of the nucleophile, being in a polar protic solvent. Alcohol is a polar protic solvent. Nucleophilicity in protic solvents increase the size of the atom, increases as the size of the atom increases. There are some polar solvents. I don't see hydrogen bonded to like oxygen or nitrogen or a fluorine atom. So these are called aprotic. We don't have an acidic proton. The proton on an alcohol is said to be acidic, just like the proton on water is acidic. Polar aprotic solvents do not have acidic protons and therefore cannot hydrogen bond. Some aprotic solvents are acetonitrile, dimethylformalamide, we call DMF, and acetone, and DMSO, dimethyl sulfoxide, not listed here. So everything we've seen in the last couple slides comes down to number 3. If you need an Sn2 reaction, you're going to want to choose an aprotic solvent. So a substrate in this chapter so far, that's been alkyl halides. In a substitution reaction, that halide leaves, and so it's called a leaving group. And we can have good leaving groups, poor leaving groups. So the best leaving groups are electron withdrawing to polarize the carbon bond to help initiate the substitution reaction. They are stable, that means not a strong base once they have left. Polarizable to stabilize the transition state. So these halides are good leaving groups because they are not strong bases. And some of these you might recognize as, if I put a hydrogen on here, we would almost have some strong acids. So these must be weak conjugate bases. So these are all good leaving groups. And these are all good leaving groups. What we don't see up here, we don't see fluoride, we don't see hydroxide. Hydroxide would be a poor leaving group because it's a strong acid. It wouldn't be stable after it left. After it left, it would grab a proton off of something, or it would want to. So we can look at the alkyl halide and decide whether it's good for an Sn2 reaction or good for an Sn1 reaction. Or we say if it's going to be involved in an Sn2 reaction, which one's best. So here is reaction rates for an Sn2 reaction. A methyl substrate is going to be the quickest, followed by a primary alkyl halide, followed by a secondary alkyl halide. Double inequality means tertiary alkyl halides do not react via an Sn2 reaction. Tertiary halides do not react via the Sn2 mechanism due to steric hindrance. So if you forgot our classification of halides, here's our methyl bromide, and here's a fast reaction rate. Here's a primary bromide, not quite as fast. Here's a secondary. This is that tertiary thing. And we said they don't react. Well, this is kind of maybe a made-up number, but it's less than 1/1000th of some relative reaction rate. Now what's going on here? These are all primary alkyl halides, but why is this one's even worse off than this thing? What's going on with neopentyl? So here's an N-butyl. It's a little less than when we have an ethyl. Why is that? These bonds rotate and it whips around like a chain, and the nucleophile's like, I need to come in and slam into this atom right here, and this chain is wiggling around. Stay away. Of course, that's not what's happening. But this effect here would be steric hindrance. Got this mess on just 2 carbons away, impeding the nucleophile from finding that carbon atom. Here it can find it. Here, it's a little more sterically stopped. So here with this space-filling model, 3 methyl groups, here comes hydroxide. It can't see its way in there very well. So notice, we have a carbon that has how many different groups on it? Hydrogen, bromine, ethyl, methyl. That means we have a stereocenter. It just doesn't go away. And so we could call this S-bromobutane. This thing slams into here. This starts to leave. Here's the transition state. This bond's forming, this bond's breaking. Notice that this now looks kind of flat and planar. And when this pops off, our stereo center has been inverted. An Sn2 reaction will result with an inversion of configuration, also called a Walden inversion. Normally at this point in the lecture I say, how many of you dainty ladies own parasols to keep the sun off you when you walk around in the Wyoming sun? And you said, none of us, it's too windy. Because what does a wind do to an umbrella in Wyoming? Have you ever played with an umbrella in the wind? And so this kind of looks like an umbrella. There's the inversion. That is a good place to stop.